Well, no, we're gonna overflow into Monday. So the most positive face I can put on this is that rotation in 3D is enigmatic. The perhaps more honest way of saying it is that 3D rotation math is just weird and kind of boring. And I'm going to try and make it less arbitrary, but then that means talking about more of it, hence 86 slides. The other thing is that there do end up being several different ways that get used to represent rotations, and you will see code, like Unity has interfaces for using all of them. So we need to at least tell you about all of the arguably bad representations that get used before we talk about quaternions, which are the ones that are really used internally. But then quaternions are just like something that a mathematician came up with on a bad LSD trip. And so they're very weird. All right, so let's back up and set some context. You've got an object in 3 space. How do you specify its position?
X, Y, Z.
Okay. Now, you made a very natural assumption in that. Yeah.
You specify it as a 4 transform matrix. It's like rotation through projective space.
Well, right. You also made you made somewhat less of an assumption. So you assumed that position meant where's it translated to, right? But in some sense, the sort of the informal notion of position, like if you haven't taken physics or vector math class, then you think of this as being a different position than this, and this as being a different position than this, and this as being a different position than this. And so the term that often gets used, so if we want to take position to mean movements you can make in the object, then short of like setting fire to it. Setting fire to it gives it a different shape, but that's probably not what you mean. That means there's all kinds of things you can do with an object to move it, to change its shape. You can translate it, rotate it, stretch it, bend it, various other things. And so when we're talking about where a 3D object is, we're really not just talking about position in the sense of where's the center of the mass, where's the translation, but what's its pose. So this is the term that artists would use. If you come from a formal physics background or from an ME background, you might use the term configuration. And you talk about the configuration space of an object. It's all the different position, orientation, shapes that the object can be in. It's all the different results of all the different motions that you can perform on it without destroying it. And different kinds of objects have different configuration spaces. So point particles, why did we start out spending all that time talking about the physics of point particles? Because they have nice, simple configuration spaces. Their configuration spaces have 3 degrees of freedom because all there is the center of mass. And in 2D, they only have 2 degrees of freedom. But if you think about water, water has an infinite dimensional configuration space, because you can bend it infinitely into literally any shape, as long as there's a container to hold it in that shape. When we think about objects in 3D in games, we're usually thinking about rigid bodies or articulated rigid bodies, i.e. stuff like this. And rigid bodies, single rigid bodies that aren't articulated, what you can do with them is translate them and rotate them. So how do we represent the configuration space of a rigid body? Well, your first thought might be, oh, you represent the configuration of a rigid body by where is its center of mass and which way is it facing, right? Now, what's the problem with that? That doesn't actually work. Yeah.
I forgot I can't talk. You can like flip yourself like.
Yes. Yes. My facing direction right now is this direction. My facing direction right now is the same facing direction. And if we imagine me levitating a little bit, then I could have the same center of mass that I had a moment ago in the same facing direction, and yet I'm clearly in a different configuration. So, facing direction loses a degree of freedom in the rotation. Because there's rotation about the facing direction that gets lost. Nevertheless, position plus facing direction is oftentimes a really useful representation of pose for objects in games, because oftentimes it's enough. If you have a first-person shooter and you have characters running around, they're sort of controlled by gravity, and so really their configuration space is where are they standing on the plane and what's their 2D rotation in the plane. But short of their getting shot and falling down, that sort of covers all of their configurations. So, but when we want to handle the general case, then what we end up doing is we say for our model, we are going to choose some reference configuration, and that is going to be the normal configuration, and any other configuration gets represented as some transformation from that. And in particular, the transformation is a translation plus a rotation. So your pose is the translation plus the rotation that's required to bring you from the reference pose to the pose you're actually in. Good? And so then the question is, of course, how do we represent those things? Well, the translation is easy, because the translation can just be a vector. Or if you want to be fancy, it can be a translation matrix. But the translation just has 3 degrees of freedom. Rotation is a huge pain in the ass, and that's why we have 86 slides in this deck. So there are a lot of ways of representing rotations in 3 space. There's axis plus angle. Here's an axis I want to rotate around. Here's the number of degrees I want to rotate around it. That's the rotation I'm performing. There's a rotation vector where the axis you're rotating around is the direction of the vector, and the angle you're rotating through is the magnitude of the vector. There are rotation matrices. There are Euler angles, which you may have run into in the documentation of Unity, but probably don't know about. Although, just out of curiosity, how many of you have run into Euler angles before? Okay, a few. All right. How many of you understand Euler angles? I'm impressed. All right, so suffice to say, all of those representations suck in a sense that we can be technical about and will be technical about. But let's go through each of them in turn. So for axis plus angle, Euler, who's kind of a big name in math in general, but especially in the development of geometry and rotational geometry in particular, proved his rotation theorem, which says in 3 space you can represent any rotation as being specifically a rotation around one axis by a specific angle. So if you take an object and you spin it around in some arbitrary sequence of rotations, the end result is the same as if you just rotated it around one axis by a fixed angle. Now, figuring out what that one axis is and what the rotation around it is, that can be a pain in the ass. But Euler proved that there had to be an axis angle decomposition of whatever the final rotation was. So that then means if we want to represent a rotation, and therefore an orientation, we can do that by somehow representing what axis it is rotated around relative to the reference configuration and what angle. So how do we represent the axis? That's sort of the hard part. The angle isn't easy, but it's not as bad. So representing a direction in 3 space, the direction has 2 degrees of freedom. And so you, of course, would like to think that you could represent it using just 2 numbers, and you can do it using just 2 numbers. You can use longitude and latitude, for example. But the problem with them is that then you have discontinuities and various other misbehavior of your coordinate system because, for example, the North Pole doesn't really have a longitude. The North Pole has, like, depending on how you want to think about it, all longitudes or no longitudes, because it's a singularity in the transform from positions to or from directions to this particular representation. And that's because when you're representing the direction as 2 angles, the 2 angles interact with one another. You can't completely decouple them the way positions in a Euclidean space, you know, your x-coordinate and your y-coordinate. You can change the x-coordinate arbitrarily without affecting the y-coordinate, and you can change the y-coordinate arbitrarily without affecting the x-coordinate. With angles, it doesn't work that way. The angles interact with one another in very painful ways, and that just leads to all kinds of nasty technical problems. So, all right, we just lost our mic. Can you hear me if I just talk loud? All right. So the standard trick that you use is the projective geometry trick that we've been talking about repeatedly, which is to say we're trying to represent a 2-degree of freedom thing that's really spherical. How do we do that? We use 1 extra number. We use 3 numbers and normalize them so that they have to sum to 1. So we use unit vectors in 3 space to represent directions. Good? And that's ultimately, if you think about it, the same hack that we use in projective geometry. So that gives us a way of representing the axis. And so the axis can be a unit vector of the angle from the scalar. The rotation vector, we use a rotation vector representation. You just have the unit vector for the axis you're rotating around times whatever your angle is, yay. And then the other person besides Rodriguez, who's sort of a really big name in the development of rotation, is Rodriguez. And Rodriguez was the first person to come up with a formula for how you figure out, given a point in 3 space, where does it actually came up with this formula without the benefit of people having invented vectors before. So he didn't actually write it in this form. This is what we would call it today. But this is what he came up with. And it's essentially the obvious thing you would do for small values of the word obvious. You're saying it's going, if you're rotating v, there's going to be a component in the direction of v, and there's going to be a component perpendicular to v, and there's going to be a component that's perpendicular to both of those. And those components are going to be sine and cosines. And you beat your head against it long enough, and you come up with Rodriguez formula. And that's awesome. Given an axis omega represented as a unit vector that you want to rotate around, and an angle in radians that you want to rotate by, this is the rotated coordinates of a point D that's rotated by that angle around that axis. Okay. So we have a way of representing rotations and computing rotations also using axis and angle or rotation vector or whatever you want to use, or whichever of those you want to use. And they have advantages and disadvantages. The advantages are it's simple by the standards of rotation math. It's compact. You're only using 3 numbers or maybe 4 to represent what the rotation is. So it doesn't take up very much RAM. That's very good. And it's basically as efficient as you're going to find for computing what the answer is. That's also good. Here's why it sucks, though. It sucks because you can't say, given this axis angle representation for rotation and that axis angle representation for rotation, give me the axis angle representation of what happens if I rotate by this and then I rotate by that. There's no no nice formula for how to combine those rotations together to get the equivalent axis angle rotation or the composition. I mean, you can do it, it's very painful. It's painful enough that I've never actually seen someone write down what the formula would be. More importantly, if you're in our field, you can't interpolate between 2 rotations. Why do you care about interpolation? Because we care about animation. We care about, we have some file someplace that says when our character is shaking someone's hand, they're in this configuration at this point in time, and they're in that configuration at that point in time, and they're in that configuration at that point in time. We have to interpolate. We have to smoothly do some linear interpolation of those poses. And that means if we have one axis angle for this position and another axis angle for this position, the axes are going to be a little different. We can't just take the average of the axes and the average of the angles and get a rotation that's halfway between the original axis angle and the ending axis angle. In fact, we may get a rotation that's entirely unrelated to either of the rotations. So axis and angle representations give us no good way of doing animation. All right. Another representation that gets used a lot in games especially, because if, for example, you're implementing something like a tank sim, it's a very natural representation to use, is yaw, pitch, and roll. So you define 3 axes. Yaw is going to be rotation around the y-axis. Pitch is going to be rotation around the x-axis. And then roll is rotation around the z-axis. first, and then yaw, and then roll, you actually get different ending configurations for the same set of angles, depending on
Rendering completed.
rotations are. And it's still hard to compose, and you still can't interpolate it really. But there's also a deeper problem. And the deeper problem has to do with the non-commutativity. So let's say we do yaw, then pitch, then roll. What happens if my pitch angle is 90 degrees? Then my yaw, I'm rotating around the vertical axis. That's what I did first. Then for my pitch angle, I turn 90 degrees. And so now my roll axis is pointing down into the ground. In other words, it's parallel to the axis I started out yawing around. And so now I've lost a degree of freedom because my roll number is actually rotating around exactly the same axis my yaw number was rotating around. And so I can only specify rotations around that axis. We've lost a degree of freedom. That comes up in basically every attempt to represent rotation that uses less than 4 numbers. And it's called gimbal lock for reasons that will be clear in a minute. And it's something that does actually matter in games. So an example that gimbal lock will come up, for example, if you're making a tank simulation and you're giving the player controls for changing their viewpoint in terms of yaw and pitch. So then I can yaw around, that's great, and I can pitch. But if I pitch all the way up, now I kind of can't yaw around anymore because any further rotations I do are just spinning me around like that. And sorry, got a little dizzy. What happens is your players get A, disoriented, and B, frustrated. So yaw, pitch, and roll is great, basically as long as you don't pitch too much. As soon as you pitch too much, things break down. You get gimbal lock. So is gimbal lock a problem? Well, it depends on your application. Again, if you're doing something like a first-person shooter, where you just like Doom, where you just have characters running around in the plane, then you can represent the configuration in terms of position in the plane and actually just their yaw angle, because that's all that they're kinematically capable of doing. And so yaw, pitch, roll is fine. And you can represent their viewpoint in terms of position, yaw, and pitch, and just leave roll set to 0 and it's all good. But if you're trying to do something like a space sim, where the ships can go into really arbitrary rotations, and you need to have a physics system computing arbitrary tumbling of objects around arbitrary axes, then it breaks down. You just can't use that representation. Yeah?
So, just about the previous slide, that was talking about gimbal lock. So
Yeah.
if the second angle is 90 degrees and it rotates the last axis to be the same as the first axis, this is probably a stupid question, but why doesn't the first axis also rotate out of the way?
Just think of it this way. I mean, that's not a stupid question. This is legitimately confusing stuff. So my rule is I always rotate first around the y-axis, that's yaw, then around the x-axis, which is pitch, then around the z-axis, which is roll. But I'm changing my notion of x and z-axis as I apply the previous transformations, right? So I'm always rotating around exactly the same axis on my first rotation, right? It's always y. But then if I rotate too much on my second one, my rotation around the x-axis, then I rotate my forward axis, my z-axis, so that now is the original y-axis.
Okay. Got it. Which is also why it's not commutative.
Yes. Yes. Ultimately, all of these problems are because rotations don't commute with one another. And so as soon as you decide you're going to do a representation that's in terms of rotate about this axis, then rotate about that axis, then rotate about that axis, those rotations around the individual axes don't commute with one another, and so you have these problems. Yeah?
What about global axes?
So
Yeah.
you mean, can you come up with a representation that's locked in terms of the global axes? And the answer is kinda.
Like, instead of like letting the axes move to each other, why don't you just rotate the object in 3 dimensions? Like, why don't you do rotation in 3 planes?
Right. It may be that you can't do that, although I can't offhand figure out what the counterexample that would show why there would be certain rotations you could express that way, but there might be. But let me talk about what you do, what you see get used a lot in games to get around the problem of order dependence of the angle, and that is Euler angles. So Euler angles, right, exactly. So here's the idea of Euler angles. For Euler angles, you're going to have x, y, and z in whatever your original orientation was, and you're going to have x, y, and z in your new orientation. Let the original x, y, z be lowercase x, y, z. Let the new x, y, z be capital X, y, z. Then there's an xy plane in your original axes and an xy plane in your new axes. Those two planes intersect with one another in a line. The Euler angles are the angle between, you call that line n. The intersection between my xy plane to begin with and my xy plane afterward. The Euler angles are the angle between your old x and the line, the angle between your new and old z-axes, and your angle between the line and the new x-axis. That turns out to be a representation that you can use to represent any rotation. For any rotation, you can come up with these 3 angles, and they uniquely characterize the rotation. This has some advantages. It's still compact, and the nice thing is the angles aren't order dependent anymore. So they're not locked to the global coordinates, but they're not based on axes that are changing as you're doing subsequent rotations. On the other hand, the disadvantages are all of the original ones. They're not composable, they're not interpolable, they have gimbal lock. And in addition, they're just bizarre, and you wonder how Euler came up with them. Whereas Yalkich and Roll is at least intuitive. So if you didn't know already, the word gimbal, that's what this means. So if you're watching Westworld and you see that poor person who's trapped in or that poor robot who's trapped in the thing that's spinning around, that's a gimbal. And gimbals are used the major use case for gimbals that I know of is when you're on a ship and you don't have GPS and you want to know what direction you're pointing, you can use a gyroscope that's heavy in spinning to stay spinning in the same direction no matter how the ship changes. But then you need to hold it up in the air somehow so that as the ship turns, it's not applying torques to try and move the gimbal, try and move the gyroscope out of position. So if you put it in one of these combinations of rings with hinges on them, called a gimbal, then the ship can rotate around the gyroscope, and the rotations of the ship don't affect the gyroscope. Now, the problem you run into is that from time to time, if you do the wrong series of motions, these rings will line up with one another. And when they line up, then the gimbal mechanism has lost the ability to rotate in some direction. And that's why it's called gimbal lock. It's actually, I'm pretty sure the phrase gimbal lock comes from NASA, because the original, like the lunar lander mission, the way they knew what direction the spacecraft was pointed was they had one of these things. And if you're on a ship, then gimbal lock isn't a problem, because mostly all the ship is doing is rotating around one axis. But if you're in a spaceship, then you're rotating around all two axes, and there would be times when they would literally physically hit gimbal lock. And the NASA missions actually had it scheduled that they pre-computed at what points along the trip they would encounter gimbal lock. And they would schedule in that at those moments they would, as fast as possible, turn off the navigation computer, reach in, move the rings out of position, and turn the navigation computer back on. It was insane. All right, so that's what gimbal lock is. Ultimately, it comes down to this basic problem that we talked about at the beginning of the quarter of having difficulty representing things like circles and spheres in terms of things like numbers, because numbers have the topology of a line, or if you have a bunch of them, the topology of like a plane or a cube or what have you. Numbers don't wrap around, and angles do. Circular and spherical things wrap around, and so there's no way to represent circular and spherical things without having some kind of horrific discontinuity, unless you do the projective geometry trick of adding an extra degree of freedom in and then restricting yourself to unit vectors. Okay? And so then the big question is going to be, what's the unit vector version of rotations? And we are going to get to that. We're not going to get deep into it today, but we'll finish up on Monday. But when we talk about, when you read about quaternions in the Unity documentation, that's the four-dimensional unit vectors that are being used. All right. So, but before we get to that, the one representation that's used that we haven't talked about, and that is indeed a good representation, is rotation matrices. So Rodriguez's formula here, if you look at it, this is a multiple of B, and so it's linear in B. This turns out to be linear in B also. If you just change B, the cross product is linear in both its arguments. So if you hold or make a constant and change B, get something that's linear in it. And similarly, dot product. So this is the sum of three quantities that are all linear in V's. The whole thing is linear in V, which means you can write it as a matrix, because we showed that all linear functions can be represented as a matrix. And you can write it out. This is what the matrix is. It's the cosine times the identity matrix plus, and then you can write cross product out as a matrix. Write that. This mess. Add all those matrices together, and you get a matrix. That's the rotation matrix for rotating about axis of omega by angle of theta. Yay! It's a mess. But it's also the thing that your GPU actually knows how to compute, right? Because your GPU basically is this big dot product engine, and so it wants to think of everything in terms of matrices. And so sooner or later, your rotations are, however they're computed originally, are going to end up as rotation matrices, because that's how the graphics backend knows how to handle them. All right. Advantages and disadvantages. The cool thing, no gimbal lock. There is no gimbal lock with rotation matrices because they are redundant representations. We're using 9, or if we're using 4x4 matrices, 16 numbers to represent something that really only has 3 degrees of freedom. So you don't end up with a gimbal lock problem. There are no discontinuities. And it's easy to compose the rotation. That's awesome, because if you want to know what's the result of doing this rotation and then doing this rotation, it's take the rotation matrix for the first one, take the rotation matrix for the second one, multiply them together, you now have the rotation matrix for the composition. And it also turns out that people with no free time, with no social life, have figured out what the rotation matrix formulae are for converting every other representation of rotations into rotation matrices. And then the people writing graphics libraries like Unity have gone and copied those all out of textbooks and written C code to do it for you. So you can, no matter what graphics library you're using, it will have a method to convert anything, any representation of rotation into a matrix. Although it probably won't have a method to go the other way, because that's hard. The disadvantages of it are uses more memory. It's much less efficient in terms of memory. And you still can't interpolate. If you take the rotation matrix for this rotation and the rotation matrix for this rotation, and you average them, sort of number by number, add the two matrices, divide by 2, you get something that not only is not halfway between those two rotations, it's not even a rotation matrix. So, you get some matrix that corresponds to some weird stretching and squishing of things. So, if you really, really want to, you can average them and then do a Gram-Schmidt decomposition to compute an orthonormal mumble with it. And that's better, but it still isn't good. It still does not look, it still looks like there's something wrong in your animation. So, this is kind of the state that people were in the 1700s, except that no one had really invented vectors or matrices before, especially not matrices. And so they were trying to figure out how to think about rotation, and they'd come up with Rodriguez's formula, but they didn't have any good thing for free space. But what they did have was a good representation for rotations in 2 space. And that was imaginary numbers. And as we talked about before, imaginary numbers are weird and non-intuitive, but strangely enough, they ended up getting accepted by many mathematicians before those mathematicians even accepted negative numbers as being valid numbers. And the reason is, as we've talked about before, but I would totally understand you're not remembering. The reason is that although for the quadratic formula, you have the nice property that if a quadratic equation has real roots, then the quadratic formula gives them to you and doesn't have any imaginary numbers in it. Cubics, there are actual cubics. This is the evil cubic equation that forced European mathematics to accept imaginary numbers. Cardano came up with the formula for solving things of this form. Here. And for this particular cubic, you have the property that it has the solution x equals 4. But Cardano's equation for it has square roots of negative numbers in it. It's kind of a problem. But at what later on Bombelli showed that if you pretend that has to be a real number, and if you pretend that it has to have the form of a real number plus some multiple of I, some multiple of the square root of -1, and you grind it out, it turns out that the plus bi and the minus bi cancel, and Cardano's formula actually gives you the right real valued answer, so long as you accept that the imaginary intermediate results are real things and are allowed to cancel with one another. And so people ended up accepting complex numbers, and you can then through associativity and distributivity write what the rules are for addition of them and then for multiplication of them. And notice that for multiplication, you get one of these skew symmetric terms like we see with cross products and wedge products, which might seem kind of familiar, but in fact, this is the wedge product in 2 dimensions. So if we say all of our numbers can be represented as complex numbers, then we can draw them in the plane. And somebody, I think it might have been Euler, realized that multiplying something by I rotated you by 90 degrees. And eventually, Euler figured out that we could write everything as polar coordinates. And multiplication of polar coordinates, of numbers in polar coordinate form, multiplied the magnitudes and added the angles. And in particular, Euler figured out that if you work in complex numbers, eta I times some angle is the cosine of the angle plus I times the sine of the angle. And he figured that out. I'm sure you've all seen this before. You may not remember. Does anyone remember how he proved this? Because it's kind of non-obvious. Yeah.
Taylor expansions?
Yeah. You just write out the Taylor series for e to the I phi, and you write out the Taylor series for sine and cosine, and you can just rearrange the terms, and this ends up being this through the mere application of algebra. So that was awesome, and that lets us do. That means in the plane in 2D. We can use complex numbers to do translation using addition, scaling using multiplication by a real number, and rotation by using multiplication by a complex number. But it only works in 2D. And so then the race was on in the 1700s for who would come up with the fancier version of complex numbers that would work for 3 space. And the obvious thing to do was to say, oh, -1 now has 2 square roots. That didn't work. And we will pick up with this on Monday, and we will talk about quaternions, which were the version that did work. Have a great week.
Two didn't work.